Warning: this material has been copied or communicated to you by or on behalf of the University of Western Sydney pursuant to Part VA or VB of the Copyright Act 1968. The material in this communication may be subject to copyright under the Act. Any further copying or communication of this material by you may be subject of copyright protection under the Act.
Okay, get yourselves organised as quickly as possible, please. Welcome back. We seem to be getting less and less, but at least the ones that are going to pass are here, isn't that right? Good. Pass, at least pass, over here. All right. Okay, so we've been obviously looking at differential equations. We've looked at some first orders, we've looked at some second orders. In the second orders, we've looked at constant coefficients. And we found that if they were homogeneous, we used the lambda method, and if they're non-homogeneous, your first thought is to use the table of undetermined coefficients. We also looked at a non-constant coefficient case, the Euler-Cauchy case, and we used the M method for that. We then found that you have to use another method if it's non-homogeneous. You have to use the method of variation of parameters. Now, you can use that method for the constant coefficient case when you have to. But basically, you use undetermined coefficients when you can, because that basically ends up being a bit simpler. All other cases, that is, when it's constant coefficient, non-homogeneous, but none of the right-hand sides fit the table, then or if it's anything that's not constant coefficient, you have to use the method of variation of parameters to solve the non-homogeneous case. Okay? Good. All right, well, we're now going to extend that to not just first order and second order, but to any sort of order, and these sorts of differential equations arise in various situations. I want to show you, though, just before we get on to what is to lead us into this, you do know that if you have y double dashed plus ay dashed plus by, that's the constant coefficient homogeneous case, and you would write the characteristic equation down, lambda squared plus a lambda plus b equals 0, and you get two solutions, and if they're real and distinct, the basic solution involves exponentials. Okay, so that's the case one scenario, but they all basically involve exponentials. All right? Let me just go back. You know that if we had y dashed, the first order case, plus ay equals 0, you know that you could write that as y dashed equals minus ay, and that's just exponential growth or decay. All right? In this case, if a is positive, it's decay. But you know how to write the solution down to that straight away. You would write down that y is some constant, e, in this case, whatever that power is, minus ax. That's the first order solution. But let's look at how you would get that if we took our q from up here. The q from up here was where whatever the derivative was, that's the power of lambda that you would write. So if we just follow that here, we would say this would be lambda plus a equals 0, which gives lambda equals minus a, which, what did you do with the lambdas? You put them as exponentials. And so you'd get exactly the same answer there. You'd put that minus a up as a power, just like you put the solution to this, the lambda 1 and the lambda 2, up as exponentials there. Okay, so now, what if we had a third order differential equation? Does anybody have any ideas how we might approach that? What will the third derivative become? A lambda cubed. Okay? And what will you do with those answers to a cubic equation? You put them as powers of exponentials, basically. And how many arbitrary constants would you expect in a third order differential equation? 3. And how many answers do you generally get out of a cubic equation? 3. So it all works. Okay? You get 3 answers out of that, and you're going to have a C1, a C2, and a C3 as the general form of the solution. Okay, now I haven't proven that for you, but the proof would be very easy. The proof would be follow what we did for, in this case. What did we do? We said, well, maybe exponentials are going to be the case. Let's throw exponentials in. You'll get a third exponential derivative and a second derivative and first. You put them all in. You'll get a common factor of either lambda. You'll cancel, and you'll end up with this cubic equation. Because a third derivative, if you started with y equals e to the lambda x, a first derivative would involve multiplying by lambda. The second derivative would give you a lambda squared, and a third derivative would give you lambda cubed. So that's where that comes from. All right? So I haven't given you a formal proof, but you see that it all makes sense. And it follows the pattern, but it also makes sense from the way that we approached it last time. Okay, well, let's jump up to not just third order, but any order. So this could be 10, the 10th derivative, with a 9th coefficient and a 9th derivative and a blah, 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 all the way down to a first coefficient and a first derivative, a 0th coefficient and the 0th derivative, and this is the homogeneous case. Now, remember that this is linear, because y and all of its derivatives appear to the power 1, and constant coefficient. Some of these coefficients could be 0, so they may not actually look like there's a derivative term there or an 8th derivative term in the middle there, but they're still there hidden, even if the constant is 0. And we see that if this was 10, then we would write down lambda to the 10. Or if it was 100, we'd write down lambda to the 100 and take all of the powers down to lambda to the 1 and lambda to the 0 and equal to 0. And as long as we can solve that equation, we will get, for an nth order polynomial equation, there are in general, if you go to complex numbers, n solutions to an nth order differential equation. Sometimes they might be sitting on top of each other, sometimes they might be repeated roots, and sometimes they might be complex numbers, and even complex number repeated roots. But in general, you get the number of solutions as the power. Okay? And of course then we'll be able to write down various forms of the solution. So the first case, if all of the numbers, all of the answers that you get out of this polynomial equation are different, then we simply do what we've said. You write down e to each of them multiplied by that many constants. If this was if this differential equation was order 100, how many arbitrary constants would you expect to be in the general solution? 100. And how many constants would this give you? If there were 100 different numbers here, this would also give you 100 arbitrary constants. Right, so it all works, it all fits in together. If they're all distinct but some are complex, so you'll get these combinations of alpha plus or minus I betas, which are different numbers. Alpha plus I beta and alpha minus I beta are two different numbers, but those parts still give you, there are really two solutions there, and they give you a part of the solution that has two arbitrary constants, except the alpha and the I beta sort of combine together now, as we've seen for case 3 of the second order case, into these exponentials times a cos and an exponential times a sine. But you still see that for two solutions there, the alpha plus I beta and the alpha I minus beta, you end up with two arbitrary constants. So each solution gives you an arbitrary constant part of the general solution. All right? Now, I will say that even though this looks, reasonably simple, you're just thinking of solving a polynomial equation, if this is to the power 1, then we get some very simple equations, just like that. Okay? If it's to the power 2, then we get a quadratic equation that we have a formula for. If it's to a power 3, there is a similar formula for a quadratic equation. It's a lot more complicated and it looks pretty horrible, and basically nobody ever uses it because you put it into a computer and you get the answer out. There is another formula for a power 4 equation, that no matter what the coefficients of the quadratic equation is, you can take those coefficients like the A, B, C, D, E, throw them into the formula and you will get the answers out. But for a power 5, that is a quintic equation or higher, there is no general formula. That you can take the coefficients, that you can take each of these coefficients and just plug in and get an answer out. It's not that we haven't found one, it's that there actually isn't one mathematically, okay, for power 5 and higher. Right? So that then means that you need to start doing other things like searching for approximate solutions if you get into these situations where you've got these higher order type things. Some will be easily solved. So, for instance, if I just said that lambda to the power 5 equals 1, all right, then that's one that you can solve, fairly easily. And if it's some, but in general, if I just in general gave you any power 5 equation, there's no one formula that works for all of those types of equations. Okay, so we've got the idea. Anyway, as long as we can find the solutions, if they're all different, we can just throw them into there. So that's like the case 1 type approach, where you get different solutions and you put them in as powers of exponentials. And this part is sort of like the case 3 approach, where you have these complex conjugate combinations, pairs of solutions. You get exponential cos and exponential sine type functions out of it. All right, so here's an example. We need to check it's linear, constant coefficient and homogeneous. And it's of third order. So we're going to expect that the characteristic equation will be lambda cubed minus 6 lambda plus 11 lambda minus 6. Now this particular series of coefficients with the polynomial we'll find a number of places in the next few pages. So we'll sort of be coming back to this a little bit. But here are some approaches to solving these sorts of things if we don't know the formula for the quadratic off by heart, for the cubic off by heart, which we don't. One approach is, look, if these are all whole numbers, and if it's going to be something reasonable that I can actually factor by hand, then if you think about where this last number has to come from, if this is going to be lambda minus A lambda minus B lambda minus C, if this is going to factor like this so that we can read off that the answer to this is lambda equals A, lambda equals B, lambda equals C, then the only way you get a constant term out of multiplying all of that out, if you thought about multiplying all of that out, the only way that you could get a constant term would be when you're multiplying the A times the B times the C. Okay? So for this last number, these numbers here, if they're going to be reasonable factors, are going to be factors of this last number. Okay? So we can just look at this last number and say, well, look, what are the reasonable factors of 6? Well, they're plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. And if we substituted any of those into here, and it came out as 0, then we would know that we have a factor. In fact, we've sort of skipped the factor step. We've gone straight to a solution. Okay? So method 1 to solve these polynomial equations, higher order polynomial equations, is to just look at the last number and see what the decent factors of that last number are. So what are the factors? Well, let's start off easy. Lambda's 1. Well, if I substitute lambda 1 into there, you can follow that through, and you do get 0 when you follow that through. So that means that lambda 1 is a solution. If I put a lambda in there, and it gives me the correct right-hand side, then it's a solution. So I found that lambda equals 1. Another factor of 6 is 2, the same thing happens there. Another factor of 6 is 3, so the same thing happens there. So that actually means that this thing is the product of these factors. So one way to factor it would be to think of it at that. In fact, this actually gives you the solution straight off. In this particular case, you don't have to go through this step. But another, well, we'll leave it. I'll come back to another way to approach it in a second. So this gives you the 3 answers. Are they all real numbers? Yes. Are they all different real numbers? Yes. So it's this case where we can just substitute the 1, the 2 and the 3 straight in, and there is our general solution. Okay? Any questions? Right. What if there's... Okay, if it ended as a plus 11, that's even better, because then there's a common factor of lambda throughout that you could take outside. Lambda equals 0 will be one root, and what will be left will be a quadratic that you can solve however way. Okay? Okay, good. Next example. Things in brackets like that mean derivative. So y to the bracket n is dny dx to the n. Okay, so I think that means a fourth derivative. It's a better way than having to write 4 dashes or sometimes we might write another way of writing this might be y to the Roman numeral 4 minus 16y equals 0. That also will mean a derivative. Okay. So the characteristic equation is lambda to the power 4 from here minus 16. Note, remember this is the case. It's not 16 lambda because this is the 0th derivative, not the first derivative. Okay, so that's what we have there. Now, how would we solve this? The straightforward way to solve this would be to say lambda to the 4th equals 16. What to the 4th is the 16th? Well, that means lambda equals 2. But of course, that's not right, is it? That's only one answer out of the 4 possibilities. Okay, so we do need to be very careful. Here is one way to do it. One way to do it is to recognise that it is really something like x squared minus y squared, which you know factors as x minus y times x plus y. So in this case, the first thing squared is lambda squared, because lambda squared squared is lambda to the 4th. And the second thing squared is 4, because 4 squared is 16. So this will be the first thing minus the second thing times the first thing plus the second thing. So that's a difference of 2 squareds, factorisation. And this first thing then is again difference of 2 squareds. So the first thing is those first 2 terms. Now the second thing is also actually a difference of 2 squareds, because lambda squared plus 4 is the same as lambda squared minus 4. And then what's the square root of minus 4? 2i. Okay, and so that's why this second part is the minus the 2i and the plus the 2i. Another way to approach it would have been to have followed this through and done it correctly by saying, that in this case, if lambda to the fourth is 16, then lambda to the squared, that's taking the square root of both sides, but remembering to put the plus or minus in there, tells you that lambda squared is plus or minus 4. So out of the first one, lambda squared equals plus 4 gives you lambda equals plus or minus 2. Out of the second one, lambda squared equals minus 4. If you think about it, gives you lambda equals plus or minus 2i. Okay, so in all of the cases, you end up with these roots. Okay. So we get 4 solutions, which is what we want for the fourth order differential equation. How do we use those? Well, that's a real root, so it's just going to be as a power of x. The 2 is also a real root, so it's also going to be a power of x. These last two, however, because they're complex numbers, we think of them as 0 plus or minus 2i. So that gives me an alpha of 0 and a beta of 2. And then they get combined into this e to the alpha x. In this case, I'm going to use C3 cos beta x plus C4 sine beta x. And e to the 0x is 1. So that's why there's no e to the 0x here. With the beta as 2, you get a C3 cos 2x and a C4 sine 2x. Okay? But you still see that for the 4 roots and for the fourth order differential equation, you get 4 arbitrary constants. There are 4 parts to the fourth order solution. Any questions? Okay, good. Well, this part's hasn't been so hard. Write down the characteristic equation. For this linear, constant coefficient, third order, homogeneous, ordinary differential equation. Isn't that good? You know what all of those words mean. Just write it down. And look at it and think about how you go about solving it. Any suggestions as to your first step? Factorise the lambda out. Okay, so do that. So you'll obviously get a lambda equals 0. And then you should be able to factor that the remaining quadratic equation without looking up at the board, which everybody does, of course. Once you have those 3 values of lambda, you write down the general solution. And just as a quick check, what sort of solution does this lambda equals 0 give us? It really just gives us a constant. That actually makes a lot of sense, doesn't it? If you then think about the equation here. A constant should make this true, shouldn't it? Because the derivative of a constant is 0, second derivative, 0, third derivative, 0. So that tells us that we're on the right track. So there is a solution. And yes, you would be expected to not just leave it as e to the 0x. You'd be expected to check that is, to simplify the solution. If you happen to write these in a different order and you had different labelled constants, that doesn't matter. Okay, write the characteristic equation down. And look at it and just see if you think there's a way of handling it a little bit. Okay, so clearly lambda cubed minus lambda squared plus lambda minus 1 equals 0. How might we solve that? One way would be to do as I suggested before. The factors of minus 1 are not too many easy factors of that. There's only plus or minus 1. So that would be one idea. But we're not quite sure what to do with that afterwards. And I'll give you the alternate method in a moment. But there is a way to do this without having to... It actually works quite easily. Can anybody see it? Take out... Which part? Okay. Well, that would leave you with a lambda squared, but also then it would be equal to 1. So it wouldn't be something that you could, factor in the way that we normally do. Yep? Yeah. So if what you mean by grouping is for the first, so you're almost there, just look at the first two. Okay? This gives us a lambda squared outside of lambda minus 1 plus a 1 outside of lambda minus 1. Okay, so just a little bit of insight. You could get this idea. Then there's a common factor, so it's lambda squared plus 1 outside of lambda minus 1, and we factored it without really too much trouble, which then means, of course, that lambda equals 1 from this first one. Lambda squared is minus 1, so lambda is plus or minus I. And we could get the solution that way. Okay? But then imagine that you couldn't quite see that. It would still be possible to look at this equation and say, well, if it's going to be easily factored, then the factors will have to do with a plus or minus 1 here. So let's try lambda equal to 1, which we would do. Is 1 cubed minus 1 squared plus 1 minus 1 equal to 0? Yeah, okay, so that works. The minus 1 doesn't work. We'd also try that because that might have given us another easy factor, but it doesn't work because it's minus 1 minus another 1 minus 1 minus another 1. That gives us minus 4, so the minus 1 doesn't work. But the plus 1 does work. But what does that mean? If lambda equals 1, then it means that lambda cubed minus lambda squared plus lambda minus 1 must be equal to lambda minus 1 times something that's going to be a quadratic. Okay, think about that. If I said that 2 was a factor of 10, then that means that 10 must be 2 times something else. Okay, so lambda equals 1, plugging it into there, giving us 0, means that lambda minus 1 must be a factor, because if I plug lambda equal to 1 into there, I get 1 minus 1, which is 0, times anything is 0. So this is why it works. But that then means that this thing, which I would like to know, is this thing divided by this. Okay, so if this was 10 equals 2 times 5, then 5 is 10 divided by 2. Right? So how do I do this division then? Well, the way I do the division is to say, and in fact, I've got the notes there, but I'll do it step by step, is to say, to do what we call polynomial long division. So we write out the thing that we want to divide into. And this is the thing that I want to divide into it. And this is how we go about it. We use a thing called HMS bring down. And it's just a funny sort of way of remembering it so that it's like an old English ship. Sorry? I'm sorry? Okay. All right. So this is what we end up doing. This, and thank you. So it's a minus and then a plus. Is that what? Yeah. Cool. Thank you. Okay. So H is how many? You look at the first term here. How many lambdas are there in the first term here? How many lambdas in lambda cubed? Oh, no, not 3. How many lambdas in 3 lambda? 3. How many lambdas in lambda cubed? Lambda squared. You do one divided by the other. Okay? So, lambda cubed divided by lambda is lambda squared. Now, let's keep everything in their right columns. So, I'll write a lambda squared up there. That was the how many part. Okay? Then the multiply part is to do this. We say lambda squared times lambda is lambda cubed, and lambda squared times minus lambda is minus lambda squared. All right? So that was the multiply part. Okay? S is for subtract. Lambda cubed minus lambda cubed is nothing. Minus lambda squared minus minus lambda squared, so it's the same thing, in this case is also nothing. Sometimes it won't be. If this was a different number here, you'd get a different thing here. In this particular case, it turns out to be nothing. Okay? And then bring down is bring the next term down. Okay? So that was we've done the subtract, and then there's the bring down. And then we do the same thing again into what's left. How many lambdas into in lambda? Just a 1. Okay? And we'll keep everything in the right columns. Then we do the multiply. 1 lambda is lambda, and 1 minus 1 is minus 1. Then we do the subtraction. Lambda minus lambda is 0. Minus 1 minus minus 1 is also 0. And there's nothing else to bring down, so we stop. And then, sort of almost magically, what appears up here is the other factor. So if this was like 2 into 10 is 5, then 10 is 2 times 5. All right? So that means that lambda cubed minus lambda squared minus 1 is that thing that we were dividing into it times by the other factor equal to 0. And from that, the first term gives me this, that second term gives me the plus or minus I. Now, this one turned out to be particularly easy, just because of the constants, but if there are other numbers around here, then you would have had different things here, and this would have taken maybe a few extra lines. But one thing to note is that when you do this, this subtraction, you will always get a 0 for these first terms, because that's how they were made up. You first of all ask how many of these were in here, and then you multiplied them back. You'll always get the same thing. So when you do the subtraction for that first term, you will always get a 0 for those first terms. You might not get zeros for these second terms, however. But you should always end up with, after some set of steps, you would always end up with a 0, because this has to perfectly factor. All right, so that's the polynomial long division HMS bring down. Okay, there are the 3 answers. Is that what we expect? Well, yes, it's a cubic equation, 3 answers. Write down the general solution. Use those 3 answers, 3 roots of the characteristic equation, to write down the general solution to that third order ODE. Okay, so now is the time to check your understanding. It would be nice if in the final exam I could just do the questions on the board and you just write, yes, I could have done that. But I won't actually be there to write the answers on the board for you, so you need to be checking that you can do this stuff now. So the 1 will give us an exponential term. But the plus or minus I, we would write as alpha plus or minus I beta, with alpha equal to 0, beta equals 1, and that would give me those two trigonometric terms. So there's the lambda equals 1, and the combination of those is the lambda equals plus or minus I. Okay, so we've really dealt with cases 1 and case 3, with cases 1 and 3 here. This is case 2, when we get roots that are the same. What happened previously when we had roots that were the same? Well, in the previous case, if I had a lambda 1 equal to lambda 2, I would still write down e to the lambda, e to the first value. But the second linearly independent function that forms a basis of the solution, we get, and we haven't proven this, but we've just told you that the way to get the second one is to multiply the e to the lambda x by an x. So that would still be the case if in any of these things we'd ended up with the same, if we'd ended up with a 1, 1 there, I still would have written those two things down. But if it was a cubic equation, I might actually have ended up with a 1, 1, 1. Or if it was a power 100 equation, an order 100 equation, or a power 100 characteristic equation, I might have ended up with 51s. What do we do in that case? Well, it's really quite easy. You just keep following the pattern. You keep getting extra terms for however many repetitions there are by multiplying by extra powers of x until you get as many as you need. Okay? Now there's one other complication, is what happens if you've got a pair of complex conjugate repetitions. Okay? So this might be the case if we ended up out of there. We might have got a lambda equals a 1, a 2, a 2, and a 3. In this case, I would have written out y equals c1 e to the 1x plus c2 e to the 2x plus c2x e to the 2x for the repetition plus, that's a 3, plus c4 e to the 3x. Okay. What if, however, I'd ended up with lambda equals 1 plus or minus 2i and 1 plus or minus 2i? Okay, think about what's happening there. These are really two solutions, and these are really two solutions. So actually each solution is in fact only repeated once. But for this first solution, we would normally write down that y equals e to the 1x outside of, I'll call it c1 cos 2x plus c2 sine 2x. And that combination of two terms covers that pair of roots, the complex conjugate roots. Okay? What happens for this repetition is we would get another pair of roots, e to the x c3 cos 2x plus c4 sine 2x, except for the repetition, it also is multiplied by x. Okay? So that's really, whenever you get a repetition, whether it's for a single real root, you multiply by x, or if it's a repetition of a complex conjugate pair, you multiply the corresponding solution by x. If there were 3 of these, you'd have an extra factor of x in there as well. Okay, so you just keep multiplying by x for each either repetition of single root or repetition of complex conjugate pair of roots. And here's the example. There's the characteristic equation. Now, how did I know that it was equal to this? Well, I didn't know that it was equal to that straight off, but what's happened along the way is that you've one approach anyway is to say, well, what are the factors of 16? 1, 2, 4, 8, 16, plus or minus, any of those, and tried them, and you would have ended up that minus 2 made that 0, and in fact that would have been the only one. So you would have done the polynomial long division, and the thing that you would have, if it's lambda equals minus 2, then the factor is lambda minus minus 2 is lambda plus 2, is the thing that you would have divided into that, lambda to the 4th plus 8 lambda cubed plus 24 lambda plus 32 lambda plus 16, and found a cubic. And then having divided the 2 into the 16, that cubic would have ended in 8. And you would have looked at the factors of 8. And the minus 2 would have worked there again. So you would have done the minus 2 into that cubic. And then you would have seen it came out as a quadratic. And the quadratic would be the perfect square, also lambda plus 2. So you would have had a lambda plus 2 from here, a lambda plus 2 from the next polynomial division, and that would have left you over with a lambda plus 2 squared. So altogether you have a lambda plus 2 to the 4. Now that is actually a long way around. It obviously would take a long time. One other, so we've got the methods. Is there some way of grouping things so that it factors? Or is there an obvious factor, like a factor of lambda, that you can just take out? Can you use polynomial long division? But that can take a long time. One other approach is to just have in the back of your mind a thing called Pascal's triangle. Pascal's triangle says that if you start writing ones out, and then for middle terms, if you add the terms above, so 1 and 2 is 3, then that triangle gives you the coefficients of things like x plus y to the 0, well that's obviously just a coefficient of 1, x plus y to the 1 is 1x plus 1y, and there's the 1 and the 1. X plus y squared is 1x squared plus 2xy plus 1y squared. So there's the 1, 2, 1 that you get from here. So without having to do make all of the multiplications, we could come straight down here and say x plus y to the 5 is 1x to the 5 plus 5x to the 4y plus 10x cubed y squared plus 10x squared y cubed plus 5xy to the 4th plus 1 y to the 5, without having to do all of the multiplying out. And notice what's happened here. The powers of x are going 2, 1, 0, and the powers of y are going 0, 1, 2. So that's what's happening here. The powers of x are decreasing, and the powers of y are increasing as you go through that pattern. Now, if you start to see numbers like these numbers appearing, if you're familiar with Pascal's triangle, then obviously something that was, if I gave you lambda to the 5 plus 5 lambda to the 4th plus 10 lambda cubed plus 10 lambda squared plus 5 lambda plus 1, you could say, hang on, I've seen those numbers, the 1, 5, 10, 10, 5, 1. I've seen those numbers. I know that that would factor. What's powers of lambda are going down? What powers are going up in each of these cases? It's just a 1, isn't it? Okay, so that's the x is the lambda and the y is a 1. So this is lambda plus 1 to the power 5. Okay? Where it's slightly harder is when it's not a plus 1. What about this? Well, 16 is obviously, if this is a quadratic, if this is a power 4 equation, then what to the power 4 is 16? 2, okay? So that gives you the clue that there's maybe something to do with 2's here. So let's have a think about what this might look like. This might look like, and I'll do it back up here, this might look like lambda to the 4th, dot, 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 plus 2 to the 4th. Okay? So if I were to work backwards, 2 to the 4th, the lambda to the 4th powers are going down that way, so the 2 to the 4th powers will be going down back this way. So is there something 2 cubed? What's that going to look like? Well, 2 cubed is 8. 8 times 4 lambda gives me the 32. And then going back down again, this would be 2 squared. 2 squared is 4. 4 watts are lambda squared. 4 watts are 24. 4 sixes are 24. And then 4, 3, 2, 1. So there'd be a 2 times what? 4 lambda cubed. So now we see we've got powers of lambda going 4, 3, 2, 1, 0. Powers of 2 going 0, 1, 2, 3, 4. And what are the other coefficients? 1, 4, 6, 4, 1, which we recognise as x plus y to the 4th. So this in fact is, with an x of lambda and a y as a 2, this straight off is lambda plus 4, lambda plus 2 to the power 4 by using Pascal's triangle. Okay? So look, the reason that you might even think about that is because, normally if you came across any old equation, then it's highly unlikely that it's going to be something as simple as this. On the other hand, if it's something that you're given to do in an exam, then it might be something that works out pretty reasonably, rather than making you do 3 or 4 polynomial long divisions. Okay? So that's an approach. Now, for those of you that watch various things like Da Vinci Code and that sort of thing, you will also have seen or perhaps heard of Fibonacci numbers. These numbers also, at high school or somewhere or other, you may have seen things like NCR. These are the binomial coefficients, so-called because there are 2 things here. Bi means 2, so there are 2 things there, binomial coefficients. These tell you how many ways there are of choosing R things from N. So for instance, this is 4C0, this is 4C1, this is 4C2. So this tells me that there are 6 ways of choosing 2 things from 4, where the order doesn't matter. So you could check that. If you just wrote out 4 things and looked at the different ways of choosing 2 of them, if you wrote out 1, 2, 3, 4, how many ways can I choose 2 of them? I could say I could have a 1 and a 2, I could have a 1 and a 3, I could have a 1 and a 4, I could have a 2 and a 3, a 2 and a 4, or I could have a 3 and a 4. That's where the order doesn't matter. Okay? 3 and 4 is the same as 4 and 3. So the order doesn't matter. And how many ways were there to do that? 6. Okay? So these numbers called the binomial coefficients. And they tell you how many ways of choosing a certain number from a certain number of other things. Also, though, as I was saying, for those of you that, Da Vinci Code, that sort of thing, the Fibonacci numbers are hidden in this as well. Because if you start adding diagonals, going through like that, you get 1 for that one, a 1 for that one, a 2 for that one, a 3 for that one. The next one is 5, and the Fibonacci sequence of 0, 1, 1, 2, 3, 5, 8, 13, where I'm adding the last 2 to get the next one, is hidden in this Pascal's triangle. So if you go on the web at some stage, look up Fibonacci number or Pascal's triangle, Fibonacci numbers, then there are whole websites. And these Fibonacci numbers appear in all sorts of places in the real world. They're not just mathematical type things. They appear in nature, they appear in all sorts of different places that you will find and hopefully be amazed at if you look them up on the web at some stage. Okay, so that's a little project for you to go and do that. Okay, so the point of all of this, in fact, is if you get something like this, it's probably going to be easily done in some way, rather than being really hard in the context of this course. Outside this course, yes, you might get something that's horrible. You might eventually have to just throw it into a computer and see what the computer can make of it, and maybe even look at approximate solutions. Okay, well, here's an exercise. Write down the characteristic equation. And solve the characteristic equation and write down the general solution. Do it all. Okay, so you should have all the lambdas by now. It's that easy. You should have all the lambdas by now. But of course there's this problem of repeated roots. How are you going to deal with those repeated roots? And it's actually a good idea. You see, it just comes out like this. You take the common factor out. It's still a good idea. This is really, if you think about this, this is really lambda times lambda times lambda times lambda plus 5 equals 0. So the roots that you get are 0, 0, 0, minus 5 for each of those terms. And it's a good idea to write out all, rather than even writing out lambda as 0, repeated, or just, if you just write lambda as 0, then you're going to miss something. It's a good idea to write them out and make sure that in your final general solution, there is a term that corresponds to each of those things. Okay? So just take a moment more to think, given what we've talked about, how would you write down the general solution? If you can't do it, that's okay, but you do need to spend a little bit of time thinking about it. What were the steps? For all the different roots, you write down e to those things. So we're going to write down a y equals, we'll have an e to the 0x, and on the end out here we'll have an e to the minus 5x. But how do we deal with these middle roots? For a repeated root, what do? It's this product of x, isn't it? So there'll be a c1 times that plus a c2x, e to the 0x, plus now there's another repeated root. How will we handle that? X squared. c3x squared, e to the 0x, plus c4, e to the minus 5x. Now, is there a term for each of the roots that we've seen? Yes, 1, 2, 3, 4. It's a fourth order. It all works. Can we simplify that a little bit? Yes, of course we can, because we know that e to the 0x is 1. And if you've done that, then have a go at the next one. And once again, what is hard about this? There's nothing really in the theory that's difficult. What is hard about this is recognising basic algebraic facts. So, as I've said right from the beginning, If your algebra and calculus, basic things like, do you know the formula for the difference of two squareds, x squared minus y squared? All right? Do you know the quadratic formula? Can you do your algebra accurately? And also your basic derivatives and integrals need to be known really, really well. Okay? The reason students generally fail this unit is not because of the new work they've learned, it's because they can't do the old work that they should have learned. All right? So this is the stage now to make sure that you attend your PASS sessions, to go to all of your tutes, to go to the learning assistance units to get those skills honed more fully, to make sure you're reading the lecture notes before and afterwards, to redo all of the worked exercises and examples out of class in the 6 or 7 hours at least that you owe me each week out of class. Okay, so that's how you're going to pass. All right, well, you see that the characteristic equation is going to be lambda to the fourth plus 2 lambda squared plus 1. Now, where do we recognise those coefficients from? The 1, 2, 1. We recognise those coefficients either from the Pascal triangle or because we know that x plus 1 squared is the first thing squared plus twice the product plus the last thing squared. So that's where we have those 1, 2, 1 coefficients that we see here. Except in this case, the first thing squared, what squared gives me lambda to the fourth? Lambda squared is lambda to the fourth. Okay, so that's how we need to be able to recognise that. Now that's not hard in terms of this unit. That's hard if we haven't got our basic ideas and know really well how to factor quadratic polynomials. Now, so as soon as we see this, this tells me that I've got lambda squared plus 1 times lambda squared plus 1 equals 0. This first factor will give me lambda squared equals minus 1. So I'll get a lambda equals 0 plus or minus 1i from that. And I will also get a lambda equals 0 plus or minus 1i from the repetition. Okay, so that's what we have here. Only here, I've written it in a way that perhaps helps us to realise how we need to write the general solution down. Okay. What do we do? Well, you have a go. You see if you understand sufficiently to be able to figure out what we would write as the general solution. So the first pair of complex conjugate roots, that's just case 2 from your quadratic case. First pair is going to be e to the alpha, remember it's going to be e to the alpha x outside of the cos and the sine term. So there is the first 2 terms that correspond to that pair of complex conjugate roots. What do we do for the repetition then, is the question. You multiply that pair by a factor of x. Okay, so that is the pair that corresponds to the repetition. All good? Makes sense? But still, once again, we check. There are really 4 answers here. There's a plus or minus I and another plus or minus I, so there are 4. And we have 4 parts to the differential equation, and it was a 4th order. We have 4 parts to the solution, and it was a 4th order differential equation. Now that perhaps factors a little bit if you wanted to factor it according to cos, but you don't have to do that. You could factor that if you want to. Okay. That was constant coefficient. So constant coefficient, 2nd order, 3rd order, whatever, is the lambda method. For Euler-Cauchy equations, if I had, and we'll just do this little section, then we'll have a 5-minute break. if we have x squared y double dashed plus ax y dashed plus by equals 0, instead of the lambda method, we use the m method. We still write two factors down for this first term, except that it turns out that the factors aren't quite the same. If it was a lambda method, it would be lambda times lambda. Except for Euler-Cauchy, it turns out to not be lambda times lambda, it turns out to be m times, not m, but m minus 1. Okay? So that's the only difference. Any ideas as to what we might do if we change this to a third order Euler-Cauchy equation? It's still Euler-Cauchy because the power of x matches the derivative, if I write it correctly, all the way through. So what are you going to have out the front here? Well, let's think about it. Yes, for the constant coefficient case, you went from a lambda squared to a lambda cubed. Well, what's happening here is that the two factors here are differing by 1. Give me an alternative theory. Yes. Okay, so they're going to be three factors, except they each differ. So we'll call that, put an A there, make that a B and make that a C. Then that makes that A and B and C. Okay, so it's still three factors, except each factor differs by 1, is what happens. So we have here, there is the example there, and there it is in your notes, as you had. To prove it, we would substitute x to the power m, and the reason that these drop by 1 each time is because every time you do a derivative, what happens to the thing you bring down, and the power gets subtracted from 1. So the next derivative you do brings that subtracted 1 down again. Okay, fourth order, there it is, 4 factors of m, 3 factors, 2 factors, 1 factor. And then this then needs to be expanded out so that you can get, you'll have an m to the 4th and some m cubed terms, etc. Okay, here's the example. The x bigger than 0 tells us we don't have to use the absolute values. If we're not told that, then we'll need absolute values in each of the cases. So for this particular case, for the cubic, we have 3 factors, 4 times 2 factors, minus 5 times 1 factor, and the minus 15 if you expand all of that out. Now that, of course, is again where you need to be able to use your algebraic skills accurately. Check that you can do this. And then the question is, how do we factor that? Well, if it's going to be reasonable factors, we'd look at factors of 15. So it's going to be plus or minus 1, plus or minus 3, plus or minus 5, plus or minus 15. We find by inspection, that's that throwing them all in, that 3 works. 3 does give us 0. And then by long division, which again, so this example is sort of giving you signposts along the way as to what to aim for when you try this yourself. We find that we do the polynomial long division, we get this is the leftover factor, and this is a quadratic equation which you need to use the quadratic formula for. Once we've written that down, now remember for Euler-Cauchy, a real distinct factor gives a power of x. Complex conjugate pairs, this is alpha is minus 2, beta is 1, give us a power of x outside the bracket and causes of log of what those beta values are, x in there. So this is, that much is Euler-Cauchy case 1, and that much is Euler-Cauchy case 3. And there'll be similar ideas for case 2. And the case 2, remember, for the constant coefficient case, you ended up with exponentials and you multiplied by x to get the extra functions in the repeated cases. What did we do in case 2 for the Euler-Cauchy? Case 2 involves a power of x and then the same power of x times what? a log function. You remember? Because you know these off by heart now, don't you? All of the different cases. All right? So a repeated root, in fact, for the higher order Euler-Cauchy cases will involve powers of the log, going from log to the power 1 to log to the power 2, etc. All right? So here's, everything just follows the same pattern. There you go. You write down the characteristic equation. Three factors, two factors, one factor, no factor. So there it is. Okay. Now remember at the beginning of the lecture I said we'd come back to this, this sort of equation. This, go back and see page 50, example 1. So we've seen that before except in terms of lambdas. We know that it factors to have 3 roots. We would have looked at, you know, by inspection, etc. And so the powers are going to give us those functions of x. Now, why does it look like that? Why does it have the absolute values in there, first of all? Great, okay. So we're not told that x is bigger than 0, okay? Whereas the previous example, we were. So when we're not told that, we need the absolute values. Now, why don't I have absolute values on all of those terms? In fact, I did, but anything squared is positive anyway. Okay? So that's why that second term doesn't need the absolute values. Okay, we'll have a 5-minute break. Okay, so have a bit of a stretch. Okay, let's go. That was a good 5 minutes. So we've been looking at higher order, we've looked at constant coefficient higher order, we've looked at Euler-Cauchy higher order homogeneous. Shh, give me your attention please. What do we do if we have linear still? These things could be constants or not. The only two types that we know how to find the homogeneous for are if they're all constants or if they follow the pattern of the Euler-Cauchy equation. But what do we do if it's not homogeneous, if it's not homogeneous, some function of x here on the other side? Well, because of the linearity, and this is what makes one of the things that makes linear equations important, if we have a non-homogeneous, we can build up the general solution by finding the homogeneous solution, which has the two arbitrary constants, or the n arbitrary constants that we need for the general solution, and any particular solution that makes the left-hand side equal the right-hand side. Because this first part makes it equal to 0, and the linearity says when you substitute something that adds to something that gives 0 and something that gives the right-hand side, the solution added together gives the correct right-hand side. But it has the best of both worlds. As well as giving the correct right-hand side, it also has the right number of arbitrary constants for the general solution. Okay, now in general, these won't be constants. If they are constants, and it's one of the right-hand sides that's in the table of undetermined coefficients, then the same sort of approach will work for the table of undetermined coefficients. So this is the first thing that we have a look at, method of undetermined coefficients. Here's a higher order case, third order. Find the homogeneous equation, comes out to this. Oh look, there's that equation again, which we've just seen for a second time and now we've seen for a third time. There are the answers. This is linear constant coefficient, so the numbers go up as powers up there. That's the homogeneous solution. But of course that would take you a few extra lines if you had to do that by yourself without us having already done that earlier in the day. What's the next step? Well, the next step, if it was second order, would be, we found the homogeneous, we would find the particular solution. How would we do that if we're using the table of undetermined coefficients? We would look at the right-hand side and we would say, okay, is that in the table of coefficients? Yes or no, is it? Yes, it's an exponential. Okay, so we would say an undetermined coefficient exponential to the same power. You see they're both minus x's. And then we would substitute. Shh, please. Quiet. Substituting, we need first derivative, we need second derivative, we need third derivative. And in this case, it just means multiplying by extra factors of -1 as we go along. And then we would substitute. There's the third derivative, there's the third derivative. There's -6 times the second derivative, there's -6 times the second derivative. There's 11 times the first derivative, there's 11 times the first derivative. And -6 times the original function is there. And all of that is supposed to add to 2e to the -x. And the only way that can do it when you get all of these things together is that if a is -1/12. So check that you can do that. That means the particular solution is this because we've calculated the value of a, and the general solution is the sum of the particular and the homogeneous. Okay? Now that looks a lot shorter than it would be normally because you've got to fill in the intermediate steps. So there's exercise for you to go away, redo that by yourself, doing all of the steps. What if either one, the right-hand side isn't... Oh, sorry, just a few other comments. If this had turned out to be sines and causes or polynomials, you would have done exactly the same sort of thing again. If it had turned out to... Now remember that the other complication for the table of undetermined coefficients is that if your choice here appears back up in here, okay, then you would multiply it by x. But see, there's this extra thing. If it had appeared twice, you would have already had an x there. So what would you have had to multiply by again? An x squared. If it now actually appeared 3 times, you would have had to have multiplied by another factor of x. Okay? So that's the only other complication, is that idea of you can get further complications of multiple roots, and that means that you just keep multiplying by x further and further times until you get something that isn't in the homogeneous solution. And remember, the reason for that, let's just be very clear about this, the reason that we can't have something here that is already in the homogeneous solution is that this particular solution is supposed to give me the right-hand side. But I already know that anything in the homogeneous solution gives me, what does a homogeneous solution equal? 0, okay? So if this is in the homogeneous solution, it can't give me the right-hand side because I know it will give me 0. That's why I have to keep changing it to be multiplying by x or x squared or however far you need to go in these higher order cases. Good. Now, what if 1, this right-hand side wasn't in the table of undetermined coefficients, or 2, this equation wasn't constant coefficient? What would we do? Well, we'd still need a method of solving the homogeneous case, and the only 2 methods that we have are for the lambda method or the M method for each of those 2 type things. Okay? But in either of those cases, that is, right-hand side not in the table or left-hand side not constant coefficient, then you cannot use the method of undetermined coefficients in the table. You have to use the method of variation of parameters. Now let's get an idea of, let's remind ourselves as to where this came from. For a second order, the particular solution comes from something that's like the homogeneous solution. y1 and y2 are the parts of the homogeneous solution, and the homogeneous solution would be constant times y1 plus a constant times y2. In the variation of parameters, we allow those constants, the parameters, to vary, and we end up with a formula that says mu equals the integral of minus y2 r over w dx, and nu equals the integral of y1 r over w dx. Now, this w, remember, comes from the y1 and the y2 written across, and the derivatives written underneath. But where did that determinant come from? Can anybody remember, because you've all read the notes again a number of times in the preceding week, can anybody remember where that Wronskian came in the derivation of this method? Where did it sort of appeared in the denominator of something? Somebody's rule we were using. Yes, thank you. Cramer's rule, okay? It started with Cramer's rule when we were solving a system of simultaneous equations. But remember, for Cramer's rule, as well as the determinant in the bottom of the fraction, in the denominator, where did these top 2 terms come from? Cramer's rule not only has denominators in the bottom of the fraction, it had denominators in the top of the fraction. And those denominators, in the numerator, the top of the fraction, it also had determinants in the numerator, that is, determinants in the top. Where did those, how are those determinants related to this Wronskian? They were exactly the same, except either the first column was changed for the first variable, or the second column was changed for the second variable. That's where each of those came from. Go back and read the notes, but I'm just reminding you as to where that basically happened. If we want to expand this now to a higher order differential equation, so if I went, if I had, for instance, a y cubed plus pqr, I'll make this an s of x there, just to use a different variable. Okay? Then the particular solution would have 3 parts. So I'll say plus a sigma. The homogeneous would have 3 functions in it. The homogeneous solution would have 3 functions for the third order. And so you would have a mu and a nu and a sigma equal to something which we don't know about yet. And we don't want to have to learn new formulae for these things, but also the Wronskian would be slightly different again, wouldn't it? Instead of having a y1 and a y2, you'd also have a y3 that you could do. What would you write underneath that? The derivatives. But can we do this determinant as it is? Can you do a 2 by 3 determinant? No. What might we put as the third row? Second derivatives, exactly. Okay? Now that's obviously just following patterns, but that's what it turns out to be because maths is full of really good patterns. Okay? So that's the third order Wronskian, yeah, and I'm sure you can imagine what the 10th order Wronskian would be. Okay? But what's going to happen in the top here is that there's going to be still over this W, just like it was over W here, except this W is now the third order Wronskian. Remember that these came from determinants in the Cramer's rule, and we also can use Cramer's rule for a 3 by 3 system of simultaneous equations, and they would be 3 by 3 determinants on the top, except for the first variable, the first column is replaced by something. For the second variable, the second column is replaced by something, and now for the third variable, the third column is replaced by something. What are those somethings? Well, this is what it now looks like. For an nth order, you're going to have n terms, not just 3. Instead of just 1 times the first y1 and another times the second and 1 times the third, for each of the different parts of the homogeneous equation, you're going to have them times by something. So previously, that was the mu function, that was the nu function, etc. previously. But for higher order, this is not going to be a 2 by 2 determinant, it's going to be an n by n determinant. And so are these things on top. But we now see that writing it this way actually makes the formulae look, instead of having to learn a whole lot of different formulae that look like this, it actually makes the formula look very much the same all the way through. The R and the W is the same in all of them. And the determinant on the top is just what we need to know how to write down accurately each time. And the way that you do that is that you write the Wronskian down, which is what we've said. You write out how many y's there are and then differentiate down until it becomes a square matrix that you can take the determinant of. And then for these other W1, W2, etc., this is the rule. For W1, so that's saying J is 1, you replace the first column. Now what does this mean? Shh, please. What does this mean? This means the T for on a vector means transpose. So instead of being horizontal, it is vertical. Okay, so this means 0, 0, dot, 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 1. That's what that means. So all this, there's your Wronskian, and this rule says you get the first W up here, the W1, by replacing the first column, leaving everything else the same, replacing the first column by zeros all the way down except the last term, a 1. This W2 is the Wronskian, except the second column is zeros all the way down, and the last one, a 1. And the last one, whichever the last one is exactly the same, except the very last column is zeros all the way down, except it's a 1. Okay? Let's see if that actually works back for our original second order equation for these ones. Let's just check that this formula does the same thing. What would it say? If we use just this general approach with n as 2, this would be n as 2 is just that top determinant there, which is what we already know is the Wronskian. But this rule is now saying that we would only have those first two terms there. W1 is the Wronskian, except the first column is replaced by zeros all the way down, except the last one's a 1. The only thing here is that there's only one place to put a 0, and the last one's a 1. And the second W that appears there is the second column replaced with zeros all the way down except the last one's 1. If we now do those determinants, we do get the minus y2, which is what we want, and we do get the plus y1, which is what we want there. Okay? So, in answer to your question as to what formulae you will get in class tests, final exams, etc., you can look on the website and you'll see that the final exam formula doesn't give you the mu and the nu in that way. But it gives you the mu and the nu hidden in this general formula. Okay? Here is an example of this case. And this is where, this is where our classification skills come in. What order differential equation is it? Order? Third. Linear or non-linear? Linear. Think about why. Constant coefficient or non-constant coefficient? Constant. So to solve the homogeneous, you would use the lambda method. Okay? Homogeneous or non-homogeneous? Non-homogeneous. So as soon as you see constant coefficient, you think, could I use table of undetermined coefficients? So look at the right-hand side. Is the table of undetermined coefficients able to be used? No, it has x's and e to the x's, but not e to the x's divided by x's. So what method must we use to solve the non-homogeneous case? Variation of parameters. And now as soon as you see variation of parameters, I didn't mention explicitly in the example before, but we then need to check that it's in standard form. Because if it's not in standard form, that would change the right-hand side. Is it in standard form? Standard form means there's a 1 coefficient here. So yes, it is. Okay. So linear constant coefficient, non-homogeneous, we need to use variation of parameters because of the right-hand side, but it's in standard form. So that's important if we're going to use variation of parameters. That means that there's a 1 out the front here. So here are the steps. Find the characteristic equation. Now, where have we seen this pattern 1, 3, 3, 1 before? Whose triangle? Pascal's triangle. Can't find it. It's somewhere there. It's the third line. Okay, so that means that, well, hang on, that's possibly lambda and a 1 cubed will be lambda cubed, 3 lambda squared, 3 lambda and a 1. But look at what's happening to the signs. They're going plus, minus, plus, minus. How would I get a plus, minus type idea in here? How would I do that? Well, if I had a minus 1 there, then remember what's happening to this. This last thing is going to the 0 and to the 1. So what's minus 1 to the 1? Minus 1. And then minus 1 squared. And then minus 1 cubed. So the squared will be the plus, the power 1 and the power 3 will be the minus. So we could see that we could factor that using Pascal's triangle. That tells me that there's a 1. So the actual values of lambda are 1 and 1 and 1. It's a good idea to write them all out just to remind you. And so, because it's constant coefficient, because we categorised it correctly, the first one gives me an e to the x, the second one gives me the same e to the x times by an x, and the third gives me the x squared term. So, that's the first step, homogeneous. Second step is to figure out the variation of parameters. We've got our individual terms. We figure out the Wronskian by writing each across here. Now, what's complicated about that? It's just that you have to use product rule a number of times. Okay? So product rule a number of times. Now, that's a tough one to have to evaluate as a determinant. Remember how we do determinants, third order determinants? You pick a row or a column that you want to expand out by, and you think about the signs like this: plus, minus, that's a minus, plus, minus, plus, minus, plus, minus, plus, so that everything's alternating where you go here. So for instance, if I were to pick this first column to expand it out by, I would say the first column, the expansion is going to be plus this first term times the determinant I get from the rest, ignoring that column and that row. So I do that determinant in there times by that. And then I do minus the next term with the determinant. I get rid of the column and row that's in, and the other four terms make up a 2 by 2 determinant. Expand that out. And then plus again this, get rid of that column and that row. The other four terms make up this 2 by 2 determinant, and do it. Okay? So obviously you probably wouldn't get something as hard as that to have to expand out completely in an exam question. But that's the method. You might get something more like showing what one of these is, because these end up being different, being easier determinants to do. Because if we choose this column that's all zeros except ones, there's only one thing to do, because the first part would be 0 times something minus 0 times something else, which we don't actually have to calculate. And then the third one is simply just this 1 times the determinant of this part, getting rid of the row and column that's in. It just ends up being a 2 by 2 determinant. Okay? So that you should expect to be able to do in an exam at some stage. Similarly, here we could multiply out, we could expand out by the first column or even the first row, but the best one to choose would be the second. So the signs would be plus, minus, plus, minus. Okay? And so we would then say this is going to be minus 1 times the determinant that you get when you get rid of that column and that row. So it's the determinant of these four terms there. Except you have to remember that it's a minus. And that's what happens here. So your role is to check these last two determinants, that you could actually calculate those properly. And the third one, of course, is you would use this third column, so you would go plus, minus, plus, minus, plus. So this is going to be plus 1 times this determinant in there of those four terms there. Okay, now what does the rule say? The rule says that in each case, the Wronskian turns out to be 2 e to the 3x. This formula up here, one way of doing it would be to, you write out each of the homogeneous functions. There is y1, there is y2, and there is y3. There is w, there is w, there is w, because that's what this says in the denominator in each case, the same w all the way through. There's an r all the way through, so there is r and r and r. And the only other thing is the bits, the w1, the w2, w3 in this case. So there is, I don't have a different coloured, but that is the w1, which we see there. That's the w2, which we see there, and that's the w3. So that's how you build it up. Okay. Then the rest of this is algebra for you to check. And of course, this is one of the cases we see a little simplification is possible. That's the particular solution that you get. So this is the homogeneous, and that's the particular. But we see that the particular solution includes an x squared e to the x term. This also includes a constant x squared e to the x. So we could factor that out and we would end up with a C3 minus 3/4. Now what's a constant minus a constant? Still a constant. So instead of calling it C3 minus 3/4, we could simplify it slightly by saying that C4 is C3 minus 3/4. It's still just an arbitrary constant. Okay, so look for slight simplifications when you are using the variation of parameters method. Okay, now luckily we have a little bit of time to do a couple of exercises. The first part I'll give you, so the point of this section is to be able to figure out to do the undetermined coefficients part. So once again, we've seen this already today. This factors as perfect squares, or another way to do this would be to say lambda to the fourth equal 1 means lambda squared equals plus or minus 1. And from that you get those 4 answers. Now, how do we understand these? It's constant coefficient, so this is the lambda method and the exponential type solutions. For the homogeneous, so we've got 2 different solutions. So this is going to be a +1, a -1, and a complex conjugate pair that's going to look like 0 plus or minus 1i. So from that, you see if you could write down the general solution, given those 4 solutions, 4 values of lambda. Can you write down the general solution, given what we've talked about today? Sorting out in your mind, this is the constant coefficient case, this is the exponentials type solutions, cases 1, 2 and 3. So immediately you should have been able to write down there's going to be an e to the x term, there's going to be an e to the minus x term, and what am I going to have for the complex conjugate pair? So hopefully you've been able to get that. Okay, so really that's for the non-homogeneous case though, which this is the right-hand side. We say these are the parts. If we were using variation of parameters, they would be the parts that make up the y1, the y2, y3, y4. But are we going to use undetermined coefficients, or are we going to use variation of parameters? Undetermined coefficients, because x squared and e to the 2x are in the table. Okay? So you see if you could write down what the particular solution form is going to be, given what we know. From the table, what would you have for the x squared? And from the table, what would you have for the e to the 2x? Okay, now you should be totally sure about that by now, if you've been putting the work in. For the x squared, we get the same power of the polynomial, but we work our way all the way down to a constant. And for the exponential, we have a constant times the same power of exponential. But there's something else that we needed to check. We need to check that if any part of either of those solutions, this solution is in 2 parts, one for the polynomial and one for the exponential, if parts of either of those solutions appear in the homogeneous. Once again, why? Because the homogeneous, we know what we get when we substitute that, we get 0. But the whole point of this particular solution is to not get 0, it's to get this right-hand side. So if any part of either of these solutions is in the homogeneous, it's useless to us because we know it's going to give us 0. So we need to change it slightly. Well, are there any constants or x's or x squareds in this solution, just as functions by themselves? No, there are only these exponentials and the coses and the sines. So that one's okay. What about the exponential function? Then the question is there an e to the 2x in here? No, there isn't. Right, so, but you have checked that. And then, to substitute, we need a first derivative, we'll need a second derivative, a third derivative, and a fourth derivative. And so there they are all there for you to quickly write down. And there is derivatives, but of course you have to be able to do those accurately. You have to remember to keep on multiplying by the 2. And then you have to remember what tricky things like 4 times 2 are, because that's often where people make mistakes. And so this is all the second part of the solution for the undetermined coefficients part. And so then it's a matter of substituting it in. So that first part is the particular solution. And then we subtract, is the fourth derivative of the particular solution, and then we're subtracting off the particular solution, and all of that is supposed to be equal to x squared plus 5e to the 2x. And the only way that that can be true is if, remember that this isn't one equation in 5 unknowns, it's not an equation for x, a, b, c, d, it's an infinite number of equations in 4 unknowns, because it has to be true for all values of x. And that's why this method of equating coefficients works. So the only way that this can be true for all values of x is if the exponential coefficient matches up and if each of the polynomial coefficients match up. What are the other polynomial coefficients on the right-hand side equal to? Anybody? How many x's are there and how many constants are there? 0. Okay, so we can write down each of those constants, put them together in the particular solution, and then the whole thing is the homogeneous solution plus the particular solution with a little check to see if there's any overlap in there, and there isn't. So that's the final neat form of the general solution. Okay, so that was the exercise for constant coefficient, non-linear, higher order, non-homogeneous, but where the right-hand side fits with the table of undetermined coefficients. This afternoon we'll look at the Euler-Cauchy case and see what we have to do there. Okay, so that's it for this morning. All good?
All right.
that region.